Good afternoon. I'm Saritha Kumari, Assistant Professor, EEE Department, Institute of Aeronautical Engineering College, Dundigal, Hyderabad. Today the topic is calculation of sag with equal level supports. So the topic is based on the sag and tension. So this is mapped to course outcome 2. So basically what is meant by sag and tension in the transmission lines? Okay. So on the right side, there is a diagram which shows the diagram. There are supporting towers, supporting poles. So between them, okay. So these two vertical lines, red color. So those are the supporting towers. Okay. Between them, the conductor is suspended. That is how the transmission line, right? So between the two supports, the conductor is supported, it is suspended. So you can see that the conductor is it's like it's not a straight like tightened wire. You can see there is a some it is like it is just suspended right between the supports. So here uh, the sag, this sag comes into the picture. So what is this basically? Sag. Okay, it is defined as it is a distance between the highest point of the poles, electric poles or towers, and the lowest point of conductor. Okay, distance between the highest point, that may be okay. So you see here the two supports towers are at equal level, right? So the distance between highest point of the support, okay, tower, and the lowest point of the conductor. So this is a conductor, right? So the lowest point is this one. So it is defined as, so the highest point of the tower, okay, that means this point, right? So distance between highest point of tower and the lowest point of conductor. This is the lowest point of conductor. So this distance, okay. So this is called sag. This is called sag. Okay. Now, so tension, they're also talking about one more thing here, tension. So when a conductor is suspended between the electrical poles or electrical towers, there is the conductor is subjected to some pressure. The conductor is under some tension. Okay. So that is nothing but the tension. Of course, this tension depends on the various parameters like weight of the conductor, atmospheric conditions, okay, like that. So anyway, there is a tension also. That means the conductor, the suspended conductor between the towers is under tension. Now, here they are telling that about this tension, there are 2 points we can see here. The tension at any point on the conductor acts tangentially. So if we take, this is the conductor between the two poles. So at any point, if we take, so this point may be this point or this point, okay, okay, what wherever, okay, the tension is, it acts, they're telling it acts tangentially. So that means like this, okay, like this, or other direction also. So, but anyway, it acts tangentially. And next point is the horizontal component of tension is constant throughout the length of the wire. So, the horizontal component of this tension is constant. That is a point throughout the total length of the wire. So, that is the point about tension. Okay. And then in the diagram, we see there are few more words like the ground clearance, okay, span. Okay, what is this ground clearance? The distance between the ground, okay, where the poles, electrical towers are placed. The distance between the ground and the lowest point of conductor, okay, this distance is called ground clearance. And span. Span means the distance between the electrical poles. So that means from here to here. Okay, the distance between the two electrical poles, electrical towers, is called span. So these are the uh, basic idea about the sag and tension. Okay, so now next, what are the factors? What are the factors affecting this sag? Okay, so we came to know sag is the distance between the highest point of tower and the lowest point of the conductor suspended between them. Now, what are the factors affecting the sag? First one, conductor weight. Sag of the conductor is directly proportional, okay, to the conductor weight. So it is related directly proportional. Sag increases with the increase in the weight of the conductor. And here, generally, the weight of the conductor increases due to ice loading, means during winter season. In winter season, where there are some countries, we know where in winter season there is a ice, okay, snow falling. So during those weather conditions, winter weather conditions, there may be a ice coating, okay, there may be a ice coating on the conductor, okay, on the in the overhead transmission lines. So during that case, the weight of the conductor is going to increase. Okay, so that is the main point, one important point, how the conductor of the conductor is increased. Okay, so it increases due to ice loading. Okay, next, second point, span. Okay, span means we know distance between the electric poles, right? Sag is directly proportional to square of the length. Okay, square of the span length. So it is also directly proportional. Okay, sag, um, but it directly proportional to with square of the span. Okay, it varies with square. So that means if we increase the span 2 meters, then let us say the sag is going to increase by 2 power 2, 4 times it is going to affect. So that is how it is directly proportional. So longer span gives more sag. Okay. Next, third one, tension. The sag is here inversely proportional. The sag is inversely proportional to the tension in the conductor. So that is how the tension is related with the sag. Next, fourth one, wind. So how the wind affects? So it increases sag in the inclined direction. Okay, of course, if because of the wind, uh, there is a wind, the sag is going to increase, but in the inclined direction. Okay, now last one, fifth one, uh, temperature. So we can say that the temperature means definitely when the temperature is more, the sag is going to increase, because conductor under higher temperatures, the conductor is going to little bit, its length is going to increase, right? So that is the case. So it increases directly, I mean directly proportional. The sag is reduced at low temperatures and increases at higher temperatures. Okay, so sag reduces at lower temperature and increases at higher temperatures. Next, we see tension. Okay, some more points about the tension. So, so see that first point, the tension at any point is we know this point already, previous slide. we have seen the tension at any point. So let us say this is the conductor, this pink color one. Okay, so the this is the support here, let us say. So of course we see in the only here we see only half part of the suspended conductor. Okay, just to see that here between the what are the point B is a nothing but electrical tower, electrical pole B. The other tower is A. Okay, so now see that here first point, the tension at any point acts tangentially, right? Okay, so tangentially. So what is tension at the middle? It may be this direction or this direction. Okay, so it is shown on the left side. Then what is the tension at the tower B, tower point, the highest point B? It is tangentially, right? So here it is shown like this. Tangential direction means, okay, the tension at point B. Point means a supporting pole. Next, second point, the horizontal component of tension is constant throughout the length of the wire. So the horizontal components of every point is same. Next, look at the third point. The tension at supports is approximately equal to the horizontal tension acting at any point on the wire. Okay, this is the point they're telling. Okay, at support means at point at support B or A, the tension is equal to approximately equal to horizontal tension acting at any point on the wire. So just that is a note. Okay, so here what is the tension at support B? We see that is the capital T. So here capital T, the tension at support B is equal to the given by T naught. Okay, so what is T naught? It is a horizontal component of the tension at lowest point of conductor O, right? So this T is equal to T naught. The tension at support B, capital T, that is equal to horizontal tension, okay, which is considered at the lowest point of conductor T naught. So that is a thing. I mean that is a point. Okay, there are two more points. Continuation. The tension is governed by conductor weight, effect of wind, ice loading, and temperature variations. So that is how the tension is affected mainly because of the conductor weight and effect of the wind, ice, okay, ice loading, and also temperature variations. Next, it is a standard practice. Next, second point, the standard practice to keep conductor tension less than 50% of its ultimate tensile strength. Okay, the point is to keep conductor tension less than 50% of ultimate tensile strength. Okay, so how much tension the conductor is under? It is given by 50% of the ultimate final strength, okay, of the conductor, of that conductor. That means here, based on that, they defined a factor, okay, factor of safety. Okay, so the minimum value of that is given by, okay, 2. That is defined as safety factor ratio of ultimate strength to actual strength, actual tension. Okay, so here so this is only 50%, right? So 50% of the actual tension. So that's why this is given by the ratio, the definition safety factor is given by okay, 50% actual tension. Okay, so the definition is given as ratio of ultimate tension to actual tension. Okay, so that is how it is defined. So based on the point, the actual thing is, okay, 50% only. 50%, if we say ultimate tension is x, this is 50% of x. Okay, so what is okay, x by 50% of x, what is that? So 2 it becomes. So the minimum value of safety factor is given by 2. So that is a meaning. Next, there are few more points, okay, related to both sag and tension. Um, so first point, the conductor sag should be kept to minimum in order to reduce the conductor material required and avoid extra pole height for sufficient clearance above ground level. So basically, that is the point. Okay, the sag is allowed to be minimum. Okay, it is nothing but it should be minimum. For what reasons? To reduce the conductor material required and also to avoid extra pole height. Okay, pole height for sufficient clearance above ground level. Okay, ground clearance, to keep ground clearance also. Okay, they want to minimize the sag. Next, second point, it is also desirable that tension in the conductor. Okay, second point I'm talking about. So the it is also desirable that tension in the conductor should be low to avoid mechanical. Second point, they're talking about the tension. They're telling that it should be also low. For what reason? To avoid mechanical failure. Okay, so that means we know that basically, when a conductor is suspended between the electric poles, it is under some pressure that is called tension. So and we know that this tension and effect depends on the, just now we have seen various factors: weight of the conductor, effect of wind, ice, and temperature variation. So we need to see that it should be low, tension should be low. Okay, so that we can avoid the mechanical failure, okay, of the conductor. Next, third point. However, low conductor tension, minimum sag are not possible. Okay, so for third point, it is telling that sag and tension both, keeping both low value is not possible. Okay, because low sag means tight wire and high tension, right? Low sag means uh, we reduce the conductor material, right? So for which results in tight wire, right, and tension more. And whereas low tension means loose wire and increased sag. Okay, low tension means loose wire and increased sag. That is a point. Okay, now so in actual practice, a compromise is made between the two. So both should be minimum. Okay, but both, to keep both minimum is not possible, right? So that is the third point, is we see that both keeping minimum is not possible. So a compromise is finally, okay, the point is there is a compromise is made between the two. Okay, while erecting a transmission line, a compromise, okay, is made between the sag and tension. Now, calculation of sag. Calculation of sag. Okay, first case, when supports are at equal levels. When supports are at equal levels. So here, see that. So this is taken from the reference, in the references I mentioned, textbook number 2. Okay, now when supports are at equal levels means both the towers. So we see in the diagram, this is electric pole, electrical tower A, next one B. So both are at equal height. Okay, that is the meaning. Equal level means above the ground they are at equal. Okay, they are provided on the same level ground. Okay, so which are equal and which are equally height. Now, so this is the case. What is a sag expression? What is a sag expression? Okay, next case 2 we have when supports are at unequal levels. That means when supports are placed at some unequal, not, it is placed on not equal levels means they may place down some hill area. One, okay, hill areas like that. That is the case two. Unequal levels means. Okay, anyway, we'll see the next case. That is the thing, unequal. So here, see that how they calculated the sag. So here initially they define small l be the length of the span. So between the two electric poles, okay, the distance is small l, and w, small w is a weight per unit length of conductor. Okay, small w is a weight per unit length, and capital T, capital T is a tension in the conductor, tension in the conductor. Okay, so initially these parameters are defined. Now Now, we see that between the two electrical towers AB, the conductor is suspended, which is shown with a pink color line. Okay, so the conductor is suspended. Okay, we know that sag is S. Okay, the highest point of the electric tower to the lowest point of the conductor. What is the lowest point here? O, right? So O is the lowest point of the conductor suspended. So the sag is S, and now here they consider a point P along the length of the conductor. They considered a point P along the length of the conductor. Okay, so here the point having this point P having the coordinates x comma y. The P, okay, it is having the coordinates from the lowest point O with respect to lowest point O. The coordinates, its coordinates are given by small x and small y. So you can see clearly the horizontal distance is marked with small x, vertical distance is mentioned with small y. Now, now here, because the this conductor between the two supports AB, this this curvature length is so small. This curvature length, okay, it looks like a curve, right? Okay, this curvature length is so small that, okay, they assume this portion OP, okay, this portion OP, okay, this portion OP is a straight line, okay, from distance from, okay, this point to this point, okay. So this assumed to be a straight line. Okay, now the two forces acting on this small portion OP, the two forces, okay, they are telling there are two forces, okay, acting on this portion OP, which are given as, okay, mentioned like here you can see, okay, first one, okay, or first force A, okay, is given as the weight of the conductor W x, okay, with respect to the small portion OP, right? They're talking. So first force acting on this is the weight Wx, which is acting at a distance of x by 2 from the point O. Okay, excuse me. So that is a first force. Okay, weight of conductor Wx acting at a distance of x by 2 meters. So you can see clearly with this blue color, okay, line. So it is acting at a distance of x by 2 meters from point O. Next, second force. The second force, okay, the tension T acting at O. That is a, okay, the tension. So you can see with the blue color line again. So that is the second force which is acting at this lowest point. So these are the two forces acting on the curve length OP. Now the next step is, if we consider movements of the forces, the movements of these two forces about point O. Okay, consider the momentum of, okay, these two forces. Okay, we know that what is meant by momentum, force multiplied with the distance. Okay, so here the momentum of this tension is given by T multiplied with its vertical distance, that is Y. Okay, next, the momentum of the weight of the conductor is Wx. Okay, and its horizontal distance is x by 2. Okay, so that's why both are equal. So here they equated both. So one is vertical force, another one is horizontal one. So both are equated. So Ty is equal to Wx into x by 2. So now they are written expression for y small y is equal to Wx square by 2t. Wx square by 2t. Now we want what is y? That is at point P. At point B, the coordinates, right? So point P is we have taken along the length of the conductor. Okay. So now we want, okay, we want from the highest point of the tower. Okay. So because we know that sag is calculated from the highest point of tower to the lowest point of conductor, right? So that's why we want to calculate the, what is y? Y means vertical distance, okay, which is parallel to actual sag. So, but we want to write the expression for this sag, okay. So that means y is equal to s, okay. That means at the any highest point of at any support, okay. That may be support B or support A. We want to, with respect to that highest point of support, we want to get the expression for sag. Okay. Now, so then in that case, y becomes equal to s, and x becomes will be equal to horizontal distance L by 2. Okay. So small L by 2. Okay. So because to calculate the actual sag, okay, we know that is from the sag definition. It is the distance between highest point of the tower to the lowest point of conductor. So that's why. Now, substituted for small x and small y. Here, finally, s is equal to w into small l by 2 whole square by 2t. W x l square by 8t. W l square by 8t. So, that is the expression for the sag. Okay, when supports are at equilevel. Okay, so the expression for sag is given by W L square by 8t. Okay, sag S is equal to, where W is the weight per unit length of the conductor, L is the length of the span, capital T is the tension in the conductor. Okay, so we will have the problems based on this. Okay, expression also. In the next section, I think, okay, we may do some problems. Okay, based on this expression, calculating the sag when supports are at equilevel. Okay, so now, so this is the first case one. Okay, these are my references. So I'm closing this class for now. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.